All right, so today we're going to be looking at the elemental composition of pure substances. So this is things like the percent composition of a compound, and then how we can also use that or the masses of the elements in a compound to discover the empirical formula or the molecular formula of the substance. So percent composition, remember, is just kind of taking the mass of one thing over the total mass of the sample and then multiplying it by 100 to get it to be a percent. So if we wanted just the mass percent of one element in a compound, we would take that mass of that one element divided by the total mass of the compound. If we're not given the mass, we can actually use molar mass to do this. So we would find the molar mass of that element and divide it by the molar mass of the whole compound. All right, in example 1, we see carbone is a substance that occurs in two forms, having different arrangements of the atoms, but always the same molecular formula. So it's always C10H14O. It also always has the same mass. We want to find the mass percent of each element in this compound. So they don't give us the masses of the elements or the compound in this problem. So what we need to do is use the molar masses from the periodic table. So we know carbon is 12.01, hydrogen is 1.008, and oxygen is 16.00. Next, we're going to multiply them by their subscripts. So there's 10 carbons in this formula. There are 14 hydrogens, and there is 1 oxygen. So we multiply those out, and then we can add them up to get our total mass, total molar mass of this compound, which is 150.2. So that's the total. And then to find the mass percent of each element, we take the mass of that element and divide it by the total. So for carbon, we would have 120.1 over 150.2 times 100. And we get, with rounding, 79.96% carbon. For hydrogen, we can do the same thing. 14.112 divided by 150.2 times 100. 14.112. And we wind up with 9.395% hydrogen. And then for oxygen, we can do 16.00 and we get 10.65% oxygen. So for empirical and molecular formulas, we learned about these last year. Empirical formulas are the chemical formula that is the simplest whole number ratio of atoms in a molecule. So it's basically completely simplified. It may be the true formula and it may not be. It may just be a simplification of it. The molecular formula is always the true formula. It's the actual number of each atom in a compound. So the molecular formula is typically a multiple of the empirical formula, and we can use molar masses to figure out what that multiple will be. So here's some examples of a couple of common molecular and empirical formulas. So you can see, like for hydrogen peroxide, the molecular formula is H2O2. So that's the actual number of hydrogens and oxygens in this compound. But we can see that we can reduce these. We can divide both of these by 2 to get an empirical formula of HO, which is our simplest ratio. Down here we have ethylene, C2H4. Again, we can divide both of those by 2 and get CH2. Or dextrose, a kind of sugar, C6H12O6. We can divide all those by 6 and get CH2O. So you can see how the empirical formula has been simplified. It's that simplest whole number ratio, whereas the molecular formula has been multiplied by some number. Remember that the molecular formula is the actual formula. So when we look up hydrogen peroxide, it is H2O2. The empirical formula is just a simplification. Example 2 asks us to determine the empirical and molecular formulas for a compound with these mass percents. We have 71.65% chlorine, 24.27% carbon, and 4.07% hydrogen. And the molar mass of the molecular formula is 98.96 grams per mole. All right, so we have to figure out the empirical formula first and then use this molar mass to find the molecular formula. We can use these percentages to find the empirical formula because they are just basically a ratio of the masses. So we can change these to grams so that we can use them to convert to moles. So the first step in an empirical formula problem is to take those grams and convert them to moles. If we start with percents, we just change that percent sign to grams. So remember, we convert grams to moles by using the molar mass. And we're going to do that for each of these elements. And then we can calculate them. And we will just round for sig figs right now. Okay, so we wind up with moles for all of our elements, and then we need to divide them all by the smallest. The smallest here is 2.021. So we divide all of these answers by 2.021. And then when we do that, we want to round to the nearest whole number because these answers will become our subscripts. So we just get 1, 1, and 2. And our empirical formula then will be ClCH2. Now, in order to find the molecular formula, we need to find the molar mass of this empirical formula. So we add those up using the new subscripts we just found, and we get 49.476 grams per mole. So in order to find the molecular formula, we're going to divide the molar mass we were given in the question by the one we just found to find that ratio between the empirical and the molecular formula. And we round that to a whole number as well. We get 2. So what that means is we're going to take this empirical formula and multiply it by 2 to get our molecular formula. So we multiply all of our subscripts, so we'd have Cl2, C2, H4. One way that compounds are analyzed, especially compounds containing carbon and hydrogen, is using combustion analysis. And we can use combustion analysis to figure out how much carbon and hydrogen is in a unknown sample, and then use that to find the empirical and molecular formula of the sample. So here you can see there's a compound. This is our carbon-hydrogen compound. It's heated up and oxygen is added, and when we add oxygen and heat, it combusts. And so that causes it to form water and carbon dioxide, as all combustion reactions produce water and carbon dioxide. So it goes through this process where the water is absorbed out of these products, and then the carbon dioxide is absorbed, and then any leftover oxygen will leave. And then we can measure the amount of water and carbon dioxide that is produced in this reaction. Example 3 is a combustion analysis problem. So we have a 2.04 gram sample that contains carbon, hydrogen, and oxygen, and it undergoes combustion analysis. We wind up with 4.49 grams of carbon dioxide and 2.45 grams of water being produced. We're asked to find the empirical formula. So the first thing we need to do is use ratios in order to find the grams of carbon and hydrogen that were in the original compound. So our original compound had 2.04 grams, but what we are looking at right now is the things that were produced. So we can use these to find out how much carbon and hydrogen there were, because the only thing we added during the combustion was oxygen. So to make the ratio, we start out by making a ratio of the molar masses. So carbon is 12.01, and the molar mass of CO2 is 44.01. And we're going to set that equal to X, because we don't know the mass of carbon, over the total. So on both sides here I have carbon over the total. So the molar mass of carbon over the total molar mass of CO2, and then the unknown mass of carbon that we're trying to find over the mass of CO2 that was produced. So it's a cross multiply problem, so we just multiply that to the other side. So we multiply and divide. Oopsies, typed it in wrong. And we get 1.23 grams of carbon. We can do the same thing with the water. So in this case, we have two hydrogens, each are 1.008. So our total molar mass of hydrogen in this compound is 2.016. And the molar mass of H2O is 18.016. I'm going to put another variable for hydrogen because we don't know how much hydrogen we have, but we do know the total mass is 2.45. So again, I have the molar mass of hydrogen over the molar mass of water, and then over here we have the mass of hydrogen over the total mass of water. Again, it's a cross multiply kind of problem. And when we calculate it, we get 0.274 grams of hydrogen. Okay, so we found the mass of carbon and the mass of hydrogen. Now we need to find the mass of oxygen. In order to do that, we take the total amount from the sample and subtract the amount of carbon and hydrogen, because we know the sample only contained carbon, hydrogen, and oxygen. So whatever is not carbon and hydrogen in this 2.04 grams must be oxygen. So we can add those two up and subtract it from the total. And we get 0.54 grams of oxygen. All right, so we found the grams of carbon and hydrogen, and then we subtracted to find the grams of oxygen. Now we need to find the empirical formula. So we have the mass of each of these, We just need to convert that mass to moles. So just like before, we're going to take each of these grams that we have and use our molar masses of those elements to find out how many moles we have. And again, at this stage, we still are rounding to sig figs. All right, so once we've done that, we look at which one has the least amount of moles. In this case, it's the oxygen. 0.034 is the smallest here. So we divide them all by 0.034. And this is where we round to the nearest whole number. And then we can use those answers as our subscripts for our empirical formula. So our formula ends up being C3H8O.